One of the outcomes of the bonding that we have looked at and the pictures that we're now able to draw is that we can look at free rotation and how bond type affects it. So the single bonds that we've been drawing, the sigma bonds, these allow for free rotation, and double and triple bonds, which are pi bonds, will restrict rotation around that bond. Now, of course, we need a picture in order for this to make sense. So what we're going to compare, the first molecule is this carbon, hydrogen, chlorine combo. So I've got two carbons connected to each other. Each carbon has two hydrogens and two chlorines. So if we just look at the carbon-carbon bond, and we're going to look at rotation around that carbon-carbon bond, that bond would be an sp3 on the carbon on the left, overlapping with an sp3 of the carbon on the right. So I have a picture of this. So I've got my carbon sp3 sigma bond drawn. I've also got my hydrogens and chlorines placed around that. That carbon has a steric number of 4, which is how we got our sp3. So the rest of the things around it should look vaguely tetrahedral. And same for the carbon on the other side. And so the free rotation that we're talking about, if you imagine holding the carbon and everything attached to it on the left still, and then rotating the carbon on the right, so I've got this coming forward, right? So like hydrogen comes forward, chlorine is in the plane of the paper, it would go backward. We're going to rotate that way. The overlap of the two sp3 orbitals is not affected by the rotation. So this is what we mean by free rotation. There's no change in the overlap of orbitals, so that specifically will not affect its ability to rotate around those bonds. Now, there are other factors, of course, that will get added on later when you take orgo, but for the bonding that we've looked at so far, this single bond, you would expect free rotation around the single bond. If it were a double bond, or even a triple bond, like we'll start with a double bond, we would expect restricted rotation around this. So as an example to compare, I've just taken away the two of the hydrogens from this molecule, and now I have a carbon-carbon double bond, and each carbon has a hydrogen and a chlorine. So my single bond portion of this multiple bond, I'm not going to draw a separate picture of it, but you should be able to draw a picture of the carbon sp2 overlap. And now my leftover p orbital is making the pi bond between the two carbons. If I were to hold the carbon on the left still and rotate around the carbon on the right, this would break my pi bond. So I've got this picture drawn. If I were to do this rotation, if I just rotate 90 degrees, so my p orbital on the left is still in the plane of the paper, my p orbital on the right would get rotated and come out of the paper and go back. There's no overlap. And if there's no overlap, then there's no bond. So this result is called restricted rotation. And one of the results of this is that the molecule that I drew to do this example with exists as two different forms that can be identified, can be separated, right? They are different molecules because there's no rotation around that double bond. So we have a cis version where the chlorines are on the same side of the double bond, and a trans version where the chlorines are on opposite sides of the double bond. And we don't see interconversion between these, unless you put some effort into it, because that rotation is restricted.